You know, talking about basics, concepts, especially after the lunch, makes you guys more sleepy. But I have to finish two topics today, very important in basic. One of them, link budget calculation. The other one, understanding of modulation. And then we will go for basic scenarios today. Tomorrow, more concepts, and then advanced scenarios. Link budget calculation means a type of calculation that you can find out by the distance that you have, by the type of product that you have, how much signal strength you can expect, and based on that signal strength, how much throughput you can get. Because throughput has direct deal with signal strength. Although throughput has direct deal with channel width, all of these options, all of these variables actually related together. When you increase the channel width, for sure your bandwidth will increase, but the noise effectiveness also will be more. So it's all about, all of them related together. But link budget calculation, when you want to calculate the amount of signal and throughput you can get from the link, it depends on both sides. Typically, we talk about point-to-point link, but you can apply same thing exactly in point-to-multipoint link with some other options. In a point-to-point link, in typical point-to-point link, there is a transmitter, there is a receiver. In transmitting side, there is a radio. There might be a cable and connector between, or antenna could attach directly to the radio. This is the concept we talked about it, FSPL, free space path loss. It means by propagating, by passing the distance, for sure you're going to have attenuation. In receiver side also we have the antenna, the cable between, radio. So link budget already depends on transmitter power. TX power, the amount of power that transmitter wants to propagate. Before antenna gain, before talking about antenna, we cannot say it's propagated already. The amount of signal, the amount of power that this radio produces. And then there will be a small loss because of the cable between. And gain of transmitter is important. Next is path loss, which is important. Now, in receiver side, the gain of receiver is important, Rx gain. And then, loss between transmission loss here and Rx sensitivity, the amount of signal that receiver can sense. This is RSSI or signal strength. So link budget actually related to all of these factors. Transmit power, transmitter loss, transmitter gain, path loss, receiver gain, receiver loss, receiver sensitivity. It depends on all of them. Now, path loss depends on your distance. Also, based on environmental changes, the actual calculation might be different per environment. But EIRP, I told you, EIRP is the ratio between signal you have and the noise you have. So here, EIRP is the ratio between signal strength and noise floor. It means if you want to increase the EIRP, you can increase either transmit power and antenna gain. But we recommend you to increase the antenna gain first, because transmit power, when you increase the transmit power, it increases the link budget in transmitting side. But when you increase the antenna gain, it increases the link budget in transmitting side and also in receiving side. because the amount of pipe, assume that the thickness of the pipe is more bigger, so you can receive more. When the antenna gain is high, means it's more directive, means it's more narrow, the beam width is more narrow. So EIRP means TX power plus antenna gain minus cable loss. Here we have the calculation based on real devices. In this side we have connectorized ePMP 1000 with the sector. In the other side we have the SM module, integrated module. This radio has TX power at the moment, 23 dBm. Antenna gain is 14 dBi. Because of the cable you are using, not the cable, because there's no cable, because of the connector, it still has connector. It still has connector, so there will be some like 1 dB loss. The EIRP in transmitting side is 36. Now in receiver side, RSSI receive threshold. This is threshold, not RSSI. This is not signal strength. This is the minimum lowest signal that receiver can hear to. It's minus 80, 86. Antenna gain 14 dBi. Transmission loss nothing. Transmission loss nothing because it's integrated option. You want a break? Is there skin pipe? This calculation is based on FCC power. FCC power is different with CE power, the maximum allowed power. To be careful about maximum in country. It says FCC means American standard, US standard.
Will we study about the calculation on reaching on the actual number of 36 dBm?
Which one you mean? This one? No, just the EIRP. Just as the amount of EIRP. Power, gain, loss, the ratio between 36 dBm. Not more than that.
But we will not learn how exactly did we come to this number 36.
36, it's obvious. 23 plus 14 means 27 minus 1, 6. 36. You see 23, 14, 27 minus 1, 36. This is in transmitting side. Also in receiver side, antenna gain integrated SM has 14. No loss because it has integrated antenna. No cable, no connector, so no loss. And the minimum amount of signal that this device can hear is minus 86. So the ratio in receiver side is 100, minus 100. Now, system gain is the ratio between transmitter EIRP and minimum received level. This is what we call it link budget or system gain. Link budget or system gain. Higher number of system gain means you have higher EIRP or either more threshold. So EIRP is good. Higher number of EIRP preferred means you have more gain or either more power. So by increasing both of them, by increasing either power or gain, you can increase the EIRP. But we recommend you to increase the EIRP, first try to increase gain because it affects both sides. But when you increase TX power, it affects only in transmitting side. With this link, we have the system gain 136 and minus 100 is the minimum received level. The minimum level that it can accept. But we consider that this is not good, this is low. It's low for us. How we can increase? First, changing in receiver side, changing the gain in receiving side. The only difference between this link and the other one, first one is using integrated module in SM side, The second one is using connectorized with the antenna. So antenna gain is more. As you can see, TX side is the same. Now in RX side, antenna gain of integrated is 14. Antenna gain of this device is 23 dB. As this antenna, 23. Minimum threshold is still the same. And because of the connector, we have we have 1 dB loss. So just by changing the antenna in receiver side from integrated module to connectorized, you are increasing the receive minimum level like 8 dB more. 8 dB affects this one. The difference is 136 to 144. 8 dB more. So just by changing the antenna, by increasing the antenna gain here, you can have 8 dB more. So changing the antenna is more important than increasing the power more. That's calculation for FCC, both integrated and normal, but this is the calculation of raw. Raw in Cambio means rest of the world. Because for Cambio, world divided to two things, US or rest of the world. It's like this. Mostly because of standards. So FCC, only US, rest of the world, because of the system gain, because it's different. The standard is different. Now, what affects your link? Okay, this is the system budget. This is the system gain. It's really good by our calculation. If we can get this amount of system gain, it's okay. We can achieve the throughput we want. But what affects your link? First, a distance. I told you the relation of the distance is like reverse. By increasing the distance double, you bring down the power budget, the link budget, half. By reducing the distance to half, you're increasing the the system budget double. So distance is the first to affect. Fading. Fading is also another thing to affect. We will talk about the fading and obstacles. If there would be something in the middle of Fresnel zone. Fresnel zone is also important. Fresnel zone is the zone around your line of sight. We have a slide for it, but not only the line of sight between transmitter and receiver, but the Fresnel zone should be clean. Recommendation is 60% of Fresnel zone should be clean to be able to have good transmission. For example, if this one is your link, for example, let's say this is your line of sight, which should be clear for sure. If line of sight is not clear, if a kind of obstacle would be between, they won't work, they won't connect. This is the line of sight, and this is what we call it Fresnel zone. Although there are different stages of Fresnel zone. For example, that's the first Fresnel zone, then this is the first Fresnel zone, this is the second Fresnel zone. Recommendation is 60% clearance of the first Fresnel zone, first, inner. Then you can expect a good quality. Minimum 60% should be clean to have a good transmission. So, obstacle should, even if the obstacle is not cutting the line of sight, but it's in the middle of your zone, then this is the problem. Even if it doesn't cut your line of sight. This table shows attenuation per different frequencies. ePMP is operational here, 2.4 or 5 gigahertz. Attenuation in 5 and 2.4 is this amount. As you can see, when the frequency goes higher, higher frequencies, more vulnerable about attenuation. You see, atmospheric cases, any environmental changes like rainfall, snow, fog, or anything, environmental changes affect higher frequencies too much more than lower frequencies. Here, attenuation is like this amount, or even less. But here in 24 gigahertz, 23 gigahertz, attenuation is this amount difference. So when you are installing the microwave, because frequency is very high, you need to aim to the focus to the remote side. And attenuation is also high. Effect of noise also high because you are using the big channel width instead of like 20 or 40. Once you increase your frequency usage, once you increase your frequency, also you can increase the channel width. N standard only can support up to 40 megahertz, but AC standard can support even 80 megahertz. That's the link budget calculation. It's important to have this calculation. Although there are lots of online calculators, you just need to provide your details. Signal power, gain, distance, frequency. By providing these small options, you can find it out. But another important topic is modulation. Modulation is not only for wireless technology, it's the concept of physics. Even music players, guitar players are using modulation, or voice transmission, video transmission, anything has the modulation, any type of transmission. But what is modulation? Basically, the signal should be exactly continuous. I mean, sinusoid wave should be exactly continuously in the same density and same frequency. But normally, because of the problem, environmental problems, anything, because of interference, noise, or whatever, lack of alignment, your signal is not really continuous. It's not exactly continuous. For example, because of obstacles or because of noise, it's getting like this. It needs to get like this. So there are three variables. There are change. What is the definition of modulation? Changing the properties of sinusoid wave to be able to have continuous waveform. Because of the problems, they are not really like each other. For example, higher frequencies, lower frequencies. Another problem is the phase. For example, this one ends from here, the other one starts from here. How you connect to them? This is modulation, one type of modulation. So there are three types of basic modulations, three types. So normally when you want to transmit 0, 1, signal is like this. This one represents 0. This one represents, 1 and then 0 and then 1 and then 2, 0 and then 1. So normally transmission should be like this exactly, but pulses are formed by combining frequencies. This is the real transmission, not like this. Three basic modulations. Modulation means changing the properties of signal to be able to have continuous waveform. Right now, there are three options or three properties of a signal you can change. One of them is amplitude shifting key. Shifting key means adaptation. Amplitude means adapting the frequencies. So one of them is, it needs high density, the other one needs low density. So amplitude shifting key is one of the basic modules to adapt the difference of frequencies. The other modulation is frequency shifting key. Means you are changing the frequency of the signal. What was the frequency change? All about the wavelength. Frequency change means, for example, it starts like this, but it's like this. Again, like. So different in attenuations. Here, frequency is lower, but here frequency is high. This is FSK or frequency shifting key. Amplitude, this one lower density, this one higher density. Or frequency change. You need to change the frequency. Here is lower frequency than here. Because this one represents 0, but this one should represent 1. Different frequency. Another type of modulation is PSK or phase shifting key. What is the phase shifting key? For example, this symbol, this type of signal shows 0, this type of signal shows 1. But because they are not really connected together, you cannot send 0 and 1 together. What you need to do, you just need to change the phase of this one to start from bottom to top, not top to bottom. Then you can connect them together. Like this, you cannot transmit this signal. You need to change the phase of this or change the phase of this to be able to attach them and continuously sending them. Amplitude, signal strength level, frequency, frequency levels, phase, phase positions. These are basic modulations. Now, based on these 3 basic modulations, we have some advanced modulations. Before going for advanced modulation, you need to understand the concept of OFDM, orthogonal frequency division duplexing. This is your channel. Actually, this is your real channel, but here you're consuming also. This is the middle frequency. So if you have 20 megahertz channel width, means there are more than one spectrum between to use. But you need a process to use. Assume that this is AP, this is SM. So both of them are following 20 megahertz channel width. 20 megahertz. So there are multiple spectrum. If your channel width was only one spectrum, so you didn't need to do such a thing. But because here there are more spectrum between client and access point, more spectrum between client and access point, you should be able to use them all together. How? With the help of FQDM. Means here the device should multiplex to different spectrum. In the other side should demultiplex them again. So multiplexing, demultiplexing, distributing to different spectrum, but at the end you need to have them all again. This process called OFDM, orthogonal frequency division duplexing. It's all about the duplexing because we want to use more than one spectrum between while you are using multiple spectrum, so you can increase your bandwidth. Because of this reason, the channel width has direct relation with bandwidth because more spectrum carry more data. There are 3 concepts in wireless technology. 3 concepts. One of them, we call it coding. What is coding? One is coding. The process of putting 0 and 1 into carrier signal called coding. Coding rate. You've heard about wireless satellite. You are setting up wireless satellite also. Sorry, wireless, no, satellite TV box. When you search for channel, they have coding rate. Coding rate is the amount of coding and data rate. And error correction also. So, coding is the process of putting 0 and 1 into the carrier signal. What is carrier signal? The signal should carry. This is coding. After coding, you need modulation. Why you need modulation? Because there are different types of zeros and one. For example, there is one signal shows 0. For example, assume that like this. Another one is 1. The type of signal is like this. 1, 1 is like this. 0, 0 is like this. So basically, you cannot attach them together and transmit. You need modulation. One time, you need phase modulation to change the phase. For example, change this one like this to send. This is phase change. Or frequency change, because 111 may use a more frequency. So these are the kind of conventions and bring modulation. Although those three are three basic modulations, we will talk about advanced modulation. After modulation, you need OFDM. Although modulation and OFDM happens at the same time. OFDM means multiplexing, demultiplexing, multiplexing. In this side, you demultiplex, in the other side, multiplex. So three concepts: coding, modulation, multiplexing. It happens every time. In transmitter side, it's better to not say AEP or a station. Better to say TX, RX. No matter which is access point, which is a station. We are talking about transmitting and receiving. So, when you want to transmit, you do coding, modulation, demultiplexing. In the other side, you do decoding, demodulation, multiplexing. Demultiplexing. In the other side, decoding means reading data from signal. Decoding, demodulation, and multiplexing. So you need to demultiplex here, and then you need to multiplex them. These are advanced modulation. Now, based on three basic modulations like ASK, FSK, PSK, these are not enough for wireless technology. These are enough for radio transmission, like AM, FM. This type of modulation is not enough for wireless transmission. We need advanced modulation, which is advanced version of these three basics. These are advanced modulation. Although before QPSK, there is another advanced modulation called BPSK. Let's start with BPSK. This diagram called constellation diagram. In Ubiquiti, you have this diagram integrated in the UI. When you configure Ubiquiti device, it shows constellation diagram in the first status page in Ubiquiti. Have you seen constellation diagram? When you configure in new versions, not Loco M or Nano, old Nano, the new device has constellation diagram. The first advanced modulation is BPSK. BPSK. What is PSK? Phase shifting key. So BPSK is type of PSK. What is the meaning of B? Means binary. Means at the same time you can transmit two symbols and 1 bit per symbol. This symbol can be either 0 or 1. This symbol also can be either 0 or 1. So in BPSK, you are transmitting binary symbols, means two symbols. Per each symbol, you can have only 1 bit, either 0 or 1. Depends which one you need at that time. This is BPSK, binary phase shifting key. QPSK, or quadrator phase shifting key, means quadrator means at the time you can transmit 4 symbols and 2 bits per each. So bandwidth is more. In BPSK, you can transmit 2 symbols and 1 bit per each. So finally, you could transmit 2 bits. But in QPSK, you are transmitting 4 symbols and 2 bits per each. So in here, you are transmitting 8 bits. 2 bits to 8 bits. Another advanced modulation is 16 QAM. QAM is quadrator amplitude modulation. So it's a type of ASK, amplitude modulation, but 16Q. 16 means at the same time you can transmit 16 symbols. Quadrate means per each symbol you can have 4 bits. So 16 multiplied by 4 is the number of bits which you can transmit at the same time. 64 QAM is the last available modulation in N standard, 802.11n, because ACS standard can support 256. But 64 is the last modulation in N standard, means at the same time you can transmit 64 symbols. Per each symbol you can have 6 bits. So how in N standard you can achieve more bandwidth? One of them is modulation. Another one is MIMO. Because in PG there was no MIMO. MIMO means 2 at the time. We will talk about MIMO. But in ABG there was no concept like MIMO. It came up after N. But something very important, assume that simple modulation, TX side is sending QPSK, RX side is also receiving QPSK. So when this symbol comes out of transmitter, should receive in exactly the same position in receiver side. Exactly in the same position, should be exactly here.